We will begin our last session of this conference. Our first speaker is Professor John Ellis, a distinguished scientist who hardly needs any introduction. Professor Ellis has a number of important contributions to the field of high energy physics. We thank him for accepting our invitation to speak for us at this virtual conference. On a different note, I would like to say something probably on the behalf of the Iranian community of high energy physics. I would like to extend our humble appreciation for the fact that he helped us to establish a meaningful relationship between CERN and Iran, by which many of our colleagues, youngs and not so youngs, have benefited from it, either by visiting CERN or participating in ongoing experiments. And we thank you for your efforts on that, which goes back some years ago. The title of the talk that Professor Ellis will give us is the Probing Astrophysical and Cosmology with Gravitational Waves, and I relinquish the forum for you, Professor Ellis, please.
Okay, thank you very much for that kind introduction. And I really appreciate the invitation to talk at your conference. I'm very sorry that I cannot be with you. I hope that we can meet again in person soon. And in the meantime, you can count on my continued support for the Iranian physics community and its collaboration with CERN.
One more thing, Professor Ellis. You have 15 minutes of time, and we will keep 5 minutes for possible questions and answer.
Okay, perfect.
I'll let you know.
Okay, thank you. So I'm not sure how familiar the audience is with the story of gravitational waves so far. So I thought I would start off by reviewing that. And looking at the gravitational wave spectrum, we see a gap. And I'm personally involved in a project called AEON, which is designed to fill that gap in the detection spectrum. And that would give us access to many interesting astrophysical and cosmological processes, such as mergers of massive black holes and probes of phase transitions in the early universe, and also searches for cosmic strings. So one development of that AEON project is a project called EDGE, which is a proposal for an atom interferometer in space that I'll mention briefly towards the end. However, the last thing that I would like to discuss is some very exciting news in the last week. The nanograv detector, which is a pulsar timing array, reports a possible signal, and we interpret that as maybe due to cosmic strings, and I'll come back to that at the end of the talk. Now I have to find the right place to...
Okay.
There we go.
Ellis, this is Abdullah. I think I projected your slide myself because I thought there is a kind of confusion. Either I can stop sharing and let you to share, or you can just tell me which slide you want and I just scroll.
Okay, well, thank you for that. So where do I click for the next slide?
Yeah, either you tell me and I do it, or I kind of stop sharing and you do it, because I heard there was a kind of confusion at the beginning for uploading your slides.
Okay, well, thank you very much. I'll ask you to do it then. Okay, so let's start off back in 1915, which was when Einstein proposed general relativity. And as I'm sure you know, he predicted gravitational waves the following year in 1916. And here's a picture of the front page of his paper. What's less well known is that 20 years later, he tried to withdraw the prediction. So he sent a paper to the Physical Review, which sent it out to a referee. Einstein was very upset. He said, my paper, how dare you referee my paper? But it's just as well that they did, because the referee pointed out that actually his original 1916 prediction was correct and his second paper was not correct. So actually the published version of his 1936 paper has been corrected. So anyway, everybody agrees that gravitational waves should exist. Next slide. So you probably also know that gravitational waves were detected indirectly for the first time by Hulse and Taylor. So they discovered in 1974 a binary pulsar, and they showed that the orbits of the pulsars changed over time, as you can see in the bottom left-hand panel. This change in orbit is due to the emission of gravitational waves, which cause the system to gradually lose energy. The change in orbit was measured for many years, as you can see, and it's in perfect agreement with Einstein's gravitational wave prediction, and for that, Hulse and Taylor got the Nobel Prize in 1993. And you can actually see in the bottom right-hand corner there, the Arecibo radio telescope, which made those measurements, which made that discovery, which made those measurements of the binary pulsar. Next slide, please. So those measurements were one example of gravitational waves, which we expect to have a very interesting spectrum extending over many orders of magnitude in frequency. So in the top right here, you see various astrophysical sources, including, for example, the type of binary pulsar, which was observed by Hulse and Taylor. In the bottom left-hand corner, we have the cosmic microwave background radiation. As you probably know, it's expected that there should be tensor perturbations in that background radiation, which would be, in fact, quantum gravitational waves. So, of course, gravitational waves were discovered directly a few years ago by the LIGO and Virgo detectors that you see in the bottom right, using laser interferometer. And they measured the gravitational waves emitted by binary black holes. So I'll say a little bit about developments of those detectors, and at the end, I'll talk about pulsar timing arrays, which you see at the bottom in the middle, which, as I said, I got very excited about recently. Next slide, please. So here are some pictures of the two LIGO detectors, which made the direct discovery of gravitational waves that was announced in 2016. So it consists of two interferometers, one in the state of Washington in the northwest of the United States, and one in the state of Louisiana in the south of the United States. So each of them has two arms, about 4 kilometers in length, and they look for the changing interference pattern between laser beams sent along those two arms. Next slide, please. So this shows you the principle. So you have a laser at the bottom. It sends a beam towards a beam splitter, which then sends the beam in two parts, one to the left, one to the right. They hit a mirror at the end of the 4 kilometers. They get bounced back. There are other mirrors close to the beam slitter, which can also reflect part of the beam. The beam can go backwards and forwards, increasing the effective path length. And eventually, they detect the beam as it comes through to the photodetector at the bottom right. And you can get interference patterns between the 2 laser beams, depending on fluctuations in space-time caused by a passing gravitational wave. Next slide, please. So this shows you what was observed by the 2 LIGO detectors in the autumn of 2015 and that were announced in early 2016. So the Washington detector is on the right, the Louisiana detector is on the left, and you can see that both of them see very significant fluctuations which are interpreted as a strain, so that's a distortion in space-time at the level of 10 to the minus 21 or so. In the bottom panels, in addition to the data, you see curves which correspond to a gravitational wave prediction. And you can see that the data and the prediction match extremely well. So there's absolutely no doubt they detected gravitational waves. Next slide, please. So the signal can be divided into 3 parts. So in any black hole or neutron star merger event, the 2 components start at a relatively large separation and they spiral in slowly, as is shown by the red circle on the left. As they spiral in, the distance between the 2 components decreases, the frequency increases. Eventually, they get close enough that they merge, as is shown by the second red ellipse. So there's a very short merger period, and then you've got basically one black hole blob, which rings down until eventually it adopts a symmetric configuration. So that's the third red phase on the right-hand side. So in the bottom panel, you can see how the black hole separation decreases with time, and you can see how the relative velocity increases. So the separation goes down to the Schwarzschild radius, and the velocity goes up to something like a half the speed of light. So, we're very proud of the Large Hadron Collider. Here, this is a much, much bigger collider. Next slide. So these are the signals that were observed by LIGO and its partner detector Virgo in their first observation period. So the one at top left is the one that I showed you a couple of slides back. They observed a whole bunch more. You can see the signal indicated by the light regions in the little boxes. And below each one, you can see the pattern of wiggles generated during infill, merger, and spin down. Now, the one at the bottom right is particularly interesting because this was not a merger of black holes, it was a merger of neutron stars. In the case of neutron stars, you can observe the infall over a much longer time period. As you can see, the signal extends over something like 100 seconds. And the exciting thing about that observation was that they detected an electromagnetic counterpart to the gravitational wave signal, which we'll see on the next slide. So in this picture at the bottom, you see the signal observed by the gravitational wave detectors. And in the upper part on the left, you see the signal that was observed by various electromagnetic detectors. So you see a signal from the Fermi satellite and from the Integral satellite. And they both of them observed a bump in the spectrum, a flash, which occurred a second or so after the merger. So this immediately tells us that the velocities of gravitational waves are very similar to the velocity of light. Following that, there were detailed follow-up experiments, observations, by something like 70 astronomical observatories around the world, which you can see on the right-hand side. They observed an incredible range of frequencies, radio, optical, you name it. And they built up a very detailed picture of the aftermath of the neutron-star merger, and they verified that these mergers are the origin of many of the heavy elements that we see in the universe today. So this is true gravitational wave astronomy. Next slide, please. So this is a recent compilation of the masses of LIGO Virgo black hole and neutron stars. So the black holes are shown at the top and in blue, and in the middle, in purple, you have black holes being observed by other experiments, not LIGO Virgo black holes. Other experiments have seen intermediate mass black holes. And then at the bottom, you see in yellow neutron stars. And you can see in the middle there that LIGO Virgo have observed two mergers of neutron stars, little peaks coming up at the bottom of the picture. Now, I'd like to mention also the thing which you see at the top in the middle, which is the merger of two heavy black holes weighing of the order of 60 and 80 solar masses to form a 140 solar mass black hole, the so-called intermediate mass black hole. More on that on the next slide. So this was reported earlier on this month. And as you can see, produced quite a healthy signal in the two LIGO detectors, left and middle, and in the Virgo detector on the right. So this is a triple measurement of a merger of the heaviest black holes seen so far. Next slide. So this is interesting because according to standard stellar evolution theory, at least one of those black holes should not have existed. The point is that if you have black holes weighing between about 70 and 120 solar masses, they explode through a process called pair instability, which blows off so much material that you do not get a black hole in that mass range. So there was one black hole which was in this mass gap. It merged with a slightly lighter one, and together they made a black hole which is sitting above the mass gap. So this is a very interesting measurement, and there's a lot of speculation. Maybe the astrophysicists haven't understood correctly the mass gap. Maybe there's some physics beyond the standard model which could change or remove the mass gap. Maybe those particular LIGO black holes were made by previous mergers. We don't know. Very interesting thing to follow in the future. Next slide, please. What's also interesting about this event is that a device called the Zwicky Transient Facility has apparently observed an optical counterpart. So this is a flash, which you see in the top two panels of this slide, which occurred about 50 days after the merger. Now, the physical process for that is very different from what we saw in the merger of two neutron stars earlier on. In this case, what is thought happened was that when you had this merger, the emission of gravitational waves changed the gravitational field in such a way that gas clouds nearby were shaken up and collided and produced this optical emission. And that's a process with a relatively long time scale, which is why this particular signal was seen 50 days later. So this is very exciting. It means that in the future, maybe we could observe other counterparts of these massive black hole mergers and maybe get some better insight into the physical processes. Next slide. So in the near future, there will be two more ground-based gravitational wave detectors. One in Japan called KAGRA, which is already starting operations, and another one in India, which is basically a new LIGO type detector, which should be coming online in a few years' time. And these detectors will enable much more accurate location in the sky of the direction in which it's occurred, which would be very helpful for identifying the progenitors and the physical processes involved. Next slide. In the longer term, there are ideas for putting laser interferometers in space. So one of them is called LISA, and this is a project of the European Space Agency, which has been approved, it's been funded, it's going. Another project called Tianjin is being proposed in China. I'm not sure of the financial status of this project, but it's certainly on the Chinese roadmap for future projects. Next slide. So on this slide, I illustrate the frequency range that LISA would be able to explore. So LIGO and Virgo, KAGRA, they will explore frequencies above 1 Hertz, typically 10, 100, 1,000 Hertz. LISA would observe processes at much lower frequencies, 10 to the minus 2, 10 to the minus 4 Hertz, typically. So what's that interesting for? Well, that's very interesting for observing really massive black hole mergers. And we'll come back to that in a moment. You see also on this slide, on the far left, at a frequency of around 10 to the minus 8 Hertz, you have pulsar timing arrays. Those are the PTAs at the top left there. I'll be coming back to them later on. Next slide. So I mentioned that one of the things that you can observe with LISA is mergers of supermassive black holes. So I'm sure that you don't need reminding that the Event Horizon Telescope last year published a picture of the surroundings of a supermassive black hole in the active galactic nucleus M87. So this black hole has a mass of something like 6 or 7 billion solar masses. By comparison, there's a supermassive black hole in our own galaxy, but it's a lot smaller. It's about 4 million solar masses, quite small on an astrophysical scale. Next slide. So LISA would be able to observe mergers of such black holes. But there is a gap between the frequency range of LISA, shown in red on this slide, and the frequency range of LIGO and follow-on detectors, the purple, blue, and green detectors on the right-hand side. There is a gap in the frequency coverage between ground-based optical interferometers and LISA, and that gap is very interesting because that's where you would see how supermassive black holes are formed. Are they formed, for example, by mergers of intermediate mass black holes? And there's also particle physics cosmology processes that show up in that frequency range, such as phase transitions and cosmic strings that I'll come back to. Of course, you also see in this picture that there's a second gap between the LISA frequency of the order of 10 to the minus 3 hertz and the pulsar timing array frequency of 10 to the minus 8 or so hertz. That's another story. Next slide, please. So I'm actually a member of a collaboration in the UK called AEON, which has recently got funding from the British government, which brings together a bunch of British universities. I'm now affiliated with King's College London. We're one of the participants in this project. And AEON is going to be working in partnership with a similar detector called MAGIS over in the United States. Next slide. So AEON and MAGIS have a different principle from the laser interferometers that I've been talking about up to now. Instead, they look at interference between atoms. And this is a space-time diagram of the operation of a pair of cold atom interferometers. The laser pulses hit the atoms, they excite them, they cause them to start moving, and you can detect the interference patterns due to the motion of these atoms, which are sensitive again to the modulation of the light travel time caused by gravitational waves. So the basic principle, if you like, is that the de Broglie wavelength is much smaller than the typical laser wavelength, and that enables you to be sensitive to a different frequency range. Next slide, please. So AEON stands for Atom Interferometry, Observatory, and Network. And I emphasize that we're going to be networking with the sibling MAGIS project in the United States, which has also received funding and is already under construction. And I might mention that there are other detectors around the world with a similar principle, including MEGA and ELGAR in Europe and Zyga in China. Next slide, please. So AEON is a program that proceeds in several stages. So the first stage is to construct demonstration 1 meter and 10 meter interferometers and to prepare for subsequent stages of the project. The second stage would be around 100 meters in length, and that is something that we would hope to be able to construct, say, 3 to 6 years after we start. In the longer term, we would like to build so the AEON 10 is quite small. It's a sort of basically a toy device to demonstrate the principle of atom interferometry, and we don't expect to do gravitational waves with it. But with AON 100, AON kilometer, and AON space or edge, we expect to get into the gravitational wave business big time, as I will discuss in the following slides. Next slide, please. So what's the science? What's the astrophysics, first of all? So I've talked previously about supermassive black holes. So how do you make a supermassive black hole? Nobody knows. There's lots of ideas, but we don't really know. Is it possible that when you make a galaxy, that some large fraction of the mass collapses to make a supermassive black hole all in one jump? Or is it possible that supermassive black holes are made hierarchically by putting together various different smaller black holes which coalesce in a sequence of steps and eventually make a supermassive black hole? So those are the two possibilities that you see illustrated on the slide. So in one case, you've got very massive black holes already from the beginning. But another possibility is that you start off with smaller black holes, like the ones that have been observed by Ligo and Virgo. You put them together, you make an intermediate mass black hole, you put the intermediate mass black holes together, and you make supermassive black holes. So in that case, you would expect to be able to see possibly mergers of those leftover intermediate black holes. Next slide, please. So there have been estimates of how many such mergers of intermediate mass black holes might take place. Most of them are expected to occur at a redshift less than 10. And you see here, well, in fact, most of them occur around a redshift of 5 or so. And on the right-hand side, you see the number of events per year expected in this calculation for mergers of 1,000 solar mass black holes, hundreds, 10,000 mass black holes, maybe tens, and 100,000 mass solar mass black holes, maybe some. Next slide. So this is a picture taken from the description that we published of the AON detector, showing the capabilities of detection of gravitational waves from the mergers of intermediate mass black holes. So over on the right, we've got the sensitivities of LIGO and a possible future detector in that frequency range called the Einstein telescope, ET. On the left, we have LISA, frequency 10 to the minus 2, 10 to the minus 3 hertz. In the middle, we have the gap in sensitivity, and you can see the prospective sensitivity of AON 10, AON 100, AON 1 kilometer, and in blue, the space-based detector, EDGE. So LIGO is great for detecting mergers of 60 solar mass black holes, as you can see over on the right-hand side. And LISA is great for seeing the mergers of supermassive black holes, 10 to the 6 solar masses, top left. But if you want to see the final stages of mergers of intermediate mass black holes, or around 10,000 solar masses, then you want a detector like AON. Next slide, please. So this shows the sensitivity of the AON 100 meter detector and 1 kilometer detector. So the horizontal axes in these plots shows the black hole mass in terms of the solar mass. The vertical axis is the redshift, and the different colors correspond to different signal to noise ratios. So for example, with AON 100, if you want a signal to noise ratio of 10, you might be able to see mergers of 10,000 solar mass black holes out to redshift approaching 1. With AON 1 kilometer, you could observe a merger of intermediate black holes out to redshifts of many tens. So these would be great for looking at the intermediate black hole mergers and giving us some idea how supermassive black holes were formed. Next slide. So this is a picture that compares directly the sensitivity of AON to those of LISA and LIGO and ET. So ET, I remind you, has not yet been funded. I expect it will be, but it's not been funded yet. LISA has been funded, but it won't come into operation until 2035 or so. AON, you see in the middle there, is potentially complementary to LISA and ET and goes way beyond what LIGO can do. So we're very excited about the possible capabilities of AON. At the moment, we just got funding for the 10-meter device, but we look forward to getting more funding for subsequent stages in the future. Next slide. So what you can do, in addition to just seeing a signal with the signal to noise ratio shown in the top left box, you can also determine its direction, the polarization of the gravitational waves, distance. You can estimate in advance the time to merger. You can predict when a merger will be seen with quite high accuracy, and of course you can measure the masses of the component black holes. Next slide.
John, I'm sorry, you got 10 plus 5 minutes.
Okay, well, I have to speed up a bit. So let me just mention, so I think I started at 34, I've been going for 36 minutes, so, okay. Thanks for the warning. Okay, so what can you do with these measurements besides the astrophysics? Well, you can do some particle physics. And I wrote a paper with Ville Vaskanen earlier on this year, where we showed that you could constrain the graviton mass. So if we go to the next slide, please. We found that with AON 1 kilometer, we could constrain the graviton mass to be less than 10 to the minus 24 electron volts, even more if they're heavier black holes, and with edge would be even an order of magnitude more sensitive. So these would be the most direct constraints on the graviton mass. Next slide. We can also look for gravitational waves from a first order phase transition. So that would proceed by the formation of bubbles, which percolate, they grow, they collide, and you can get gravitational waves from the collisions and from turbulence and sound waves in the plasma. So we studied a couple of models of this, one with a non-normalizable Higgs to the 6th interaction, and one with an additional U1 gauge boson Z prime. Next slide. So this is a plot that shows what the possible spectrum of such gravitational waves might be. So in this particular example, the peak of the spectrum occurs in the LISA range, but the signal could also be detected with an intermediate range detector, intermediate frequency detector, such as the space version of AON. Next slide. And this is a bunch of similar plots for models with an additional U1 gauge interaction. In this case, you see that there are many examples where the spectrum actually peaks in that intermediate frequency range. Next slide. So here you see the ranges of parameters. So the horizontal axis is the mass of this extra gauge boson. The vertical axis is its coupling. And the light colored regions are where you can detect this thing through the gravitational wave signal. On the left, we've got AON 100. On the right, we've got AON 1 kilometer. And you see that these detectors would be able to detect gravitational waves for gauge bosons with masses much larger than are accessible with the LHC or even a future circular collider. Next slide. So I already mentioned that in addition to the terrestrial AON series of detectors, we've made a suggestion for a space-based version, a sort of atom interferometer version of LISA, if you like, which is currently under consideration by the European Space Agency. Next slide. So this plot just shows you that this detector that we call EDGE would have really stupendous abilities to detect the mergers of intermediate mass black holes, extending out to redshifts of 100, 1,000. And again, you see that it would be very complementary to LISA and the Einstein telescope. Next slide, please. So another piece of particle physics that you can look at is the possibility of gravitational waves from cosmic strings. So these would produce a spectrum which is almost independent of frequency over a very large range. So here you see an example where the string tension mu is 10 to the minus 11 in Planck units. And what you see is the black curve is what you would expect without any new physics. But if you have new physics, new degrees of freedom, for example, then they would change the spectrum, as you can see by the various curves on the right-hand side. And by detecting gravitational waves and cosmic strings at different frequency ranges, you could hope to determine the evolution history of the universe back to very early stages. Next slide. So now I come to this week's excitement. So a week ago today, the nanograv pulsar timing array reported, quote unquote, strong evidence for a stochastic common spectrum process at frequencies less than 10 to the minus 8 hertz. So that's what you see on the left-hand side there. You see those 2 points at low frequencies joined by an orange dashed line. So there seems to be something there. And on the right-hand side, you see fits to their data. Let's just focus on the orange dashed one. You see that the amplitude of this signal could be 10 to the minus 15 or so. And it has a slight slope that's indicated by this parameter gamma that you see at the bottom. So a value of gamma of the order of 5 would be preferred. So such a signal could possibly come from the mergers of supermassive black holes. In that case, the prediction is along the vertical black dashed line there. Next slide. So we wrote a paper earlier on this week pointing out that these data could be interpreted in terms of cosmic strings. So in the left plot, you see a sort of a rainbow curve, which is a prediction of the cosmic string model, basically 0 parameters, as a function of the cosmic string tension, G mu. And values of G mu are shown in that color band in the middle there. So the data seem to be at slightly larger values of gamma than what you'd expect from supermassive black hole mergers, which are shown by the vertical gray line. And on that vertical gray line, you can see upper limits coming from previous pulsar timing delay experiments. So there's some tension with previous results, but not very strong. So on the right-hand side, you see what are fits to the nanograv signal at the 1 and 2 sigma level would predict over a wider range of frequencies. And you can see that they just skim along the underside of the nanograv measurements. Next slide, please. So here on the left-hand side, we see a comparison between the cosmic string models and the nanograv measurements. The spectrum is almost flat, extending up to much higher frequencies. These gravitational waves and cosmic strings will be detectable with LISA or with the Chinese proposal Tianjin, with AON, not with LIGO, unfortunately, but with the Einstein telescope and with the EDGE space experiment that we proposed. So if our interpretation of the pulsar timing array data is correct, there's plenty of things to be seen with future experiments. Next slide, please. So that brings me to the end. Experience with electromagnetic waves shows the advantages of making observations over a range of different frequencies, and the same is expected to be true for gravitational astronomy. So I mentioned the AON and EDGE projects, which are based on atom interferometry, which would aim at intermediate frequencies. I've also advertised the hint of cosmic strings from the nanograv pulsar timing array. So there's plenty of other opportunities in fundamental physics, astrophysics, and cosmology, which haven't yet been explored in detail. So I think this is unique, interdisciplinary science, and I thank you for your attention.
Thank you. That was a very interesting talk, very elaborated, and we appreciate that. We have time for a few questions. Actually, we have 5 minutes of our time. So if anybody have any question, please welcome. Any question? Comments?
This is Abdullah. Can I ask a question on one of the bullets in the summary? You mentioned atom interferometry could explore the nature of the dark matter. I might have overlooked that, but can you elaborate a little bit how the interferometry can provide us with more information about dark matter?
Yes, indeed. Thank you for that question. I decided to drop that because I was going to focus on gravitational waves, and I already had a lot to say. So ultralight dark matter would be present in the universe in the form of waves. And if that dark matter interacts with either the photon or the electron, it would cause the properties of atoms to change very, very slightly as a function of space and time. And you can use these atom interferometers to look for that effect. And it's potentially sensitive to ultralight dark matter. Not so light as to be fuzzy dark matter, but much lighter, obviously, than what you could explore with the LHC. So it would be a complementary window on dark matter. And I would suggest that if you're interested in following that up, you look at the Aeon and Edge papers that I mentioned in my talk, where we discussed that.
Thank you.
Thank you. I think there's another question. I will read it, perhaps. Mr. Mujavez is asking. The question is this: how big can a black hole get?
How big can a black hole get?
I mean, I think that it's referring to the coalescence of the smaller black holes to bigger. Is there a limit on it?
I think there's no theoretical limit. And I mentioned that M87 has a mass of several billion solar masses, and that's not the biggest one. I'm not absolutely sure, but I think the most massive ones maybe even have a mass of 10 to the 11 solar masses. I remind you that a typical galaxy might have a mass of 10 to the 12, 10 to the 13 solar masses. So there is surely some sort of astrophysical upper limit, but it's going to be well above the billions of solar masses that I mentioned.
Thank you. Any other question? Comment?
May I ask a question? Do you hear me?
Yes, Farhad, go on.
Okay. Hi, John. How are you?
I will not give you my usual greeting since this is the public.
No, then not this time. Okay. There is this question. Since all these gravitational wave experiments are basically international collaborations, and there would be this question of whether Iran could possibly participate in one of these collaborations. And you are of course, the best person to ask, as mentioned, you were the instrumental person in involvement with the CERN experiment. So, on very general ground, what are the possibilities? Which experiment, with which collaboration, etc.
Okay, well, thank you, Farhad, for that question. So, if we look at the projects that I mentioned in my talk, we've got Ligo. Now, that's an American project. I think that for Iran to participate in Ligo would be very difficult. Then we've got Virgo, which is a European project. There, I don't see any reason why Iran could not get involved at some level. And if there would be interest, I would be happy to try to broker some sort of contact with Virgo people. That's an ongoing experiment. In the near future, in your neighborhood, there will, of course, be this LIGO spin-out in India. But there again, I think there might be a difficulty because that Indian detector is based on American technology. So I think the Americans might have a word to say. There's these Chinese projects. So I mentioned Zyga, which is a terrestrial project. And I mentioned Tianjin, which is a space project. That might be worth thinking about. And then I mentioned this project, Aeon, and its space extension, EDGE, which I'm involved in. Now, speaking for myself, I would be completely open to building up some sort of connection with Iran associated with that experiment. But that's just a personal impression. I would have to talk to my collaborators. At the moment, it's a UK-funded project with only UK participants. But I talked the other day to the head of the project, and he would be open to having associate members from outside the UK.
That's great. Let's follow this up later on. Thank you.
Okay, you're welcome.
Thank you. We will move on to our next talk. Thank you, John. Appreciate it for the talk. Okay, well, thank you again very much for the invitation, and I hope to meet you again soon. Certainly. In person, inshallah. Okay.